Hi, and welcome to the final video on calculus with polar coordinates for Calculus 2. So, in this video we're going to talk about the area with polar coordinates and polar functions. Now, when we looked at it in Cartesian, we looked at the area under the curve. And while we have a way of thinking about the area with polar functions, it's not quite the same. So if we have a function f in Cartesian, the integral from a to b is going to be this area under the curve. But when we move to polar, things are a little different. So we'll have some function that's mapped from theta equals alpha all the way to theta equals beta. And to find the area here, it's kind of, the area is enveloped by alpha and beta instead of under the curve from A to B. And so the area that we're looking at is actually this blue area that's encompassed by this function. Now it still gives us an area, it's just the nomenclature that we use is slightly different. And this is where that nomenclature stops, because now we just talk about the area again. So the formula for area in Cartesian, it's just the integral from a to b of f of x dx. And when we talk about polar, we have to change it just a pinch. So we go from our angle alpha to our angle beta of 1/2 r squared d theta. And let's just emphasize that r is in fact a function of theta. So let's look at a couple of examples. In our first example, we're going to look at the area of a circle. So we want to show that the area of a circle with radius a is actually equal to pi a squared. So we're going to show that a circle with radius a has an area of pi a squared. Now, if we were to look at it in terms of Cartesian, so we would have to set up our circle, x squared plus y squared equals a squared, and then we would have to solve for either x or y, so y is equal to plus or minus the square root of a squared minus x squared, and then we could take the integral of maybe just the top half, a squared minus x squared dx, and we wouldn't want to go through the whole thing, maybe from 0 to a. So we would be looking at this, and we would be taking this area, and then we'd multiply it by 4. And then in here we would have a trig integral, and when we finally evaluate it, we would get 4 times pi a squared over 4, and then we would get pi a squared. And that is just a huge mess that we would have to go through many, many steps to deal with. But polar is a lot easier, because with polar coordinates, we don't have to divide our function into a bunch of parts. So we have the integral from alpha to beta of r squared d theta. And we can just draw a circle, the whole thing, and we can shade in the region that we want to find. So in this region, we're going from 0, which is the start point of our circle, and we're going around all the way to 2 pi, and we'll stop there. Because if we go any further, we're going to start double counting our area, and we don't want to do that, because then it wouldn't be an accurate representation of the area inside. And now we also know, well, that's 1/2. So let's pull that 1/2 on the outside, because it's just a constant. And we know that r is equal to a. So this is 1/2 a squared d theta. A is just a constant, so let's pull it out. 1/2 a squared, the integral of 0 to 2 pi of d theta. So we have 1/2 a squared times 2 pi minus 0. If we want to fill in that extra step, that is, let's go ahead and move this down. We get 1/2 a squared theta from 0 to 2 pi. And then we have 1/2 a squared times 2 pi minus 0. The 1/2 and the 2's cancel each other out. And we're just left with pi a squared. So in our first case, we kind of knew what the bounds should be. But let's take a look at an example of where we have to find the bounds for our region. Just like when we were doing the area between two curves in Cartesian coordinates. So we want to determine the area of an inner loop of r equals 2 plus 4 cosine theta. So we're going to be looking at this blue area, and I'll double hatch it with red and circle it so you can see it. So it's not quite clear what our bounds for theta should be. But what we do know is that when it first enters the loop, it's at r equals 0. And then when it exits the loop again, it's also at r equals 0. So the loop is enclosed by 2 thetas where r of theta is equal to 0. So let's go ahead and set r equal to 0 and solve for theta. So we're going to say 0 is equal to 2 plus 4 cosine theta. So theta is going to be equal to 1/2, or cosine of theta. And that tells us that theta is going to be equal to 2 pi over 3 and 4 pi over 3. And these are our bounds. Okay, there are other thetas such that that happens, but 2 plus 4 cosine theta happens over a period of 2 pi. So we're just going to pick the easy one. We'll just pick our bounds between 0 and 2 pi. So now we know that our area is 1/2 the integral of r squared d theta from alpha to beta. This guy here is our alpha, and this pink guy here is our beta. So let's just go ahead and plug everything in. So the area is 1/2 the integral from 2 pi over 3 to 4 pi over 3 of r squared. So it's 2 plus 4 cosine theta all squared d theta. And we can go through and solve the whole thing. And if you need to see how to solve this integral, you can just go ahead and look back in the trigonometric integration section, or the trig integration section, and we find that our area is equal to 4 pi minus 6 square roots of 3. And this is the area of the inside loop of that limacon. As always, if you have any questions, comments, or concerns, put them in the comments below and I will get back to you. And as always, thank you for watching.